We are going to start looking at some of the processes that continually change the Earth, starting with plate tectonics. You've already learned the different layers of the Earth. Plate tectonics is driven by how the solid outer layer, the lithosphere, interacts with the fluid layers of the mantle. The lithosphere is actually broken into several large pieces called tectonic plates that are less dense and therefore float upon the fluid mantle. These plates are held together tightly, but they are distinct plates and can move independently. Each plate includes some oceanic crust, some continental crust, and some of the mantle beneath them. The diagram shows the different plates of the Earth's lithosphere. Each again can move and change independently. The changes to and interactions of these plates, called plate tectonics, can cause earthquakes, volcanoes, reshape the landscape, and even move continents. Continents, to our eyes, seem relatively static, but they do actually move. They move slowly, so the maps you saw as a younger student are still accurate, but they have actually moved several inches since you were born. If you looked at a map of the Earth from 125 million years ago or 200 million years ago, it would look drastically different. The continents move because of plate tectonics. This movement of the continents as a result of plate tectonics is called continental drift. The land on Earth has changed drastically over the 4.6 billion years of its existence. 45 million years ago, all of Earth's land was actually part of a single supercontinent called Pangaea. During the Jurassic period, approximately 180 million years ago, it began to break up, forming two large continents called Laurasia and Gondwana. These two continents broke apart into the 7 continents we have today, which still continue to move. How do plate tectonics cause the continents to move? The plates are pressed together tightly, but at those areas where two plates meet, called tectonic boundaries, the fluid asthenosphere and solid lithosphere can interact. At some of these boundaries, called mid-ocean ridges, a process called seafloor spreading occurs. Magma forces itself up to the surface from the asthenosphere, pours out onto the old crust, solidifies, and forms new crust. As it does so, it pushes the older crust away. When this old oceanic crust being pushed away from the mid-ocean ridge butts against continental crust, it dives beneath and returns to the mantle. However, as the solid oceanic crust is pushed below the continental crust, it exerts force on the continental crust and causes it to move slightly. This slight movement over time accounts for the continental drift we now understand to occur. Many of the geologic features we commonly recognize appear as a result of the force exerted by plates colliding in this way, opposite of mid-ocean ridges. Evidence to support the theory of continental drift was initially scarce, but it has since accumulated and has come from a variety of fields. Currently, we have evidence to validate continental drift from fields such as geography, geology, climatology, paleontology, and even paleomagnetics. Geography studies the location of places around the Earth, including cities, states, and countries. These markings, though, are man-made and change as civilizations come and go and land changes from hand to hand. Looking on a larger scale and on the geologic timescale rather than a history timescale, geology can actually lend insight in support of continental drift. Looking at the continents as whole pieces, they actually seem to fit together. The east coast of South America fits snugly against the west coast of Africa. North America, Greenland, and Northern Europe fit together. Antarctica, the Indian subcontinent, and Australia all fit against the east coast of Africa. This global puzzle isn't definitive proof that continents have moved over time, but for the continents to have formed independently in such a way would have been extremely coincidental, supporting the idea that the continents were once together and have since broken apart. Adding to this geographic evidence, the distribution of rock across the Earth's surface further supports the theory of continental drift. Geology has shown rocks of the same age and physical composition to line up across the continents that geographic evidence suggests were once connected. Continental Europe and eastern North America are separated by thousands of miles. yet the rock making up the crust shares remarkable similarities. Similar patterns emerge between Africa and South America, suggesting that these currently disparate lands were once unified and have since broken apart. Climatic evidence for continental drift actually comes from observations of rock similar to geologic evidence. In this case, we're looking for evidence to show that glaciers once existed in locations that are currently far from the polar regions to which glaciers are now restricted. Such evidence exists in Australia, Africa, India, and South America, all places currently far too warm to have glaciers. India, for example, is currently on the equator, so any glacier that was there melted long ago. However, the movement of a glacier over the Earth can vastly change the landscape, creating lakes, flattening lands, or carving valleys, so evidence of their presence can be seen long after they melt. The presence of such evidence in locations such as these subcontinents of India suggests that these locations haven't always been this close to the equator, and were probably at some point actually in the polar zone. Paleomagnetic evidence comes from observations of Earth's rock, but instead of looking at the type of rock, its composition, or for evidence of massive ice erosion, in this case we're looking at the magnetic properties of the rock. Earth has a massive magnetic field, and rocks are largely composed of metals, so the rocks on Earth are influenced by Earth's magnetic field. Rocks don't slide to one pole or another, but when they are first forming, they do develop slight magnetic properties with their own north and south poles, because of the influence of Earth's magnetic field. Many of these rocks, though, are no longer aligned with Earth's magnetic north and south poles. This suggests that they have moved. Since rocks don't walk across the ocean floor or across open stretches of land, the Earth beneath them is probably responsible for this movement. Biologic evidence dating back long enough to demonstrate continental drift has to come from paleontology and the study of fossils. Fossils of the same species have been found on continents currently separated by massive expanses of ocean. Other fossils have been found in locations that currently occupy climatic zones that could not support the kind of life. Certain species of plants have been found on South America, Africa, Antarctica, Australia, and in India. Seas can travel surprising distances, but crossing the Atlantic or Indian Ocean is really unlikely. Further, Antarctica is currently covered in massive glaciers, so for plant fossils to have been found there, it must have at one time been much warmer. Fossil evidence of aquatic organisms has also been found on land, in some cases at the top of mountains. The simplest explanation for the presence of identical species on separate continents, of plants on Antarctica, aquatic organisms in mountain ranges, is that the Earth has changed. Mountains have grown, and the continents have moved. Recently, satellite tracking has actually observed the continents moving in real time, and shown the different continents to move at variable speeds, some up to a few inches a year.